for intermediate algebra 3-1B. So this is the second day. We're going to find the definition of a function and then figure out what is a function and how are the domain and range, which are concepts we talked about yesterday, important when defining a function. To start with, pause this video and try these two warm-up problems on your own to see if you remember the things that we talked about yesterday. The correct solutions or something similar to what I got. As a reminder, domain is the same thing as the input, which is generally speaking, when we're talking X and Y, it is our X values, and range is your output or your Y values. So here I've just listed out for my domain the values of X, and in my range, the values of Y. You do not have to repeat any that you see multiple times. I use these little mustache brackets or squiggly brackets. Put commas in between, just like a list. Okay, and the second one, it was an application problem like what we did yesterday. I thought about the domain being the people that are entering the theater, or the people who are getting tickets. So we can't have partial people or decimal people. So it's going to be all whole numbers, right? So no decimals. And they have to be less than or equal to 50. You could also use the vocab integers. Integers, remember, are positive and negative solid numbers with no decimals. So if you said integers, you would say 0 to 50 or something along those lines, because you would want to make sure that they were positive, because you can't have negative people either. For the range, we're talking about how much money the movie is getting. So if we had 0 people go to the movie theater, we would get $0. If we had 1 person, that would be 5. 2 people would be 10, et cetera, et cetera. So those are all multiples of 5. So I could have listed them all out, but I just used that little ... to represent the pattern. Let's move on to some new concepts for today. Let's think about this. So yesterday we talked about inputs and outputs. So here's an example that you probably would be familiar with. If I used my function machine and my rule was the output will be the number of sides, I bet you we could fill out this table. If I put in triangle into my function machine, how many sides would come out, or what would be my output? Well, a triangle has 3 sides. We all know that. How many sides does a square have? 4. How many sides does a pentagon have? 5. A hexagon has 6. This one, don't fall into the trap. An octagon is a stop sign, so that one actually has 8. Seems pretty easy, right? This is a function machine. What would you think if I changed this table up a little bit, though? And what if we lived in a world where we inputted a triangle and out we got 3 or 4 sides? Like a triangle could have both 3 and 4 sides. Wait, that doesn't seem to make sense. Or what if a square happened to have 4 or 5 sides? Like it could be either one. Or let's think about a phone number. You dial your best friend's phone number, and sometimes you get your best friend that answers. Then sometimes it's your worst enemy that answers. Like that's not what happens. Your phone number goes to that one particular person. So something's a little bit off with this table. What's happening is we have inputs in this example that are going to multiple different outputs. This does not work in functions. This is not a function. What this is an example of one input to many outputs, which is not the definition of a function. And a lot of times they will seem weird in the scenarios. The definition of a function, and this is something you're absolutely going to want to make sure you know, is every input, aka your X values, has exactly one output, which are your Y values. So this is an example right here of something that is 1 to 1. One input goes to exactly one output. Now, something can be a function and not be 1 to 1, and here's an example of that. We might have an input that's going to an output, and then another input that's going to the same output. This is actually still a function because my input, this particular input, only goes to one output. And this input only goes to one output, and that's fine. We cannot have it going the other way around. And we'll show lots of examples of this. This is an example of many to one. These phrases, one-to-one, many-to-one, one-to-many, all those, you're going to see them when you're doing your homework assignments and as we're talking, but it's not something you'll necessarily be tested on. So here are two examples of, they're the exact same thing, but this is a function. So I wanted to show you in multiple representations. Here we have it in a table, and here we have it again in a mapping. We're showing the exact same thing. So -2 goes to 4, -1 goes to -2, and so on and so forth. Some things I want you to note is that we have one arrow going from each and every input value. So this is a function because every input has exactly one output. You will see this phrase again in Pearson when you're doing your work. Y is a function of x. So y is the output. It makes sense because every x corresponds to exactly one y. Here is an example of something that is not a function. All right, so again, multiple representations. We have a table and the mapping. The mapping, I think, is visually easier to tell because if you look here, -2, that is going to both -4 and +4, all right? That's not allowed. That would be like a triangle having two different numbers of sides. It doesn't make sense. Same thing with this -1, right? In order for something to not be a function, it just has to happen one time where that you have that split. If we're looking at the table, something to notice is you see how you have these repeating x values. That is going to be a big clue that this is not a function because -2 is going to two different y values. So we can say this in a sentence similar to what we did before, or we can say y is not a function of x. Y is not an output of x because at least one x value corresponds to more than one y. They have to be exactly one in order to be a function. Let's look at the graphs of these two examples that I just did. So this first graph is an example of a function, or the one that I had just earlier. Notice it looks a lot like kind of a diagonal line if I was to connect those. And then the one on the right, we have what looks like somewhat of a sideways V. The first one is a function, and the second one is not a function. What do you notice and what do you wonder? Now, I don't know about you, but one thing that I notice about that second graph is that I have these two x values that are lined up right on top of each other. And I don't have that happening in this first example. All these points are just the only ones in that line. And that's exactly what we want you to notice. This is something called the vertical line test. We are not allowed to have 2 points that line up on the same line because that means that this x value has two different outputs or two different y values. So here are some more examples using the vertical line test. Let's look at graph A. We have this V. Do we have any points that line up directly above each other? So I'm just going to imagine me drawing this line or pulling this line across. Every single point or place on this graph, there's only one part or one point that crosses. So that is a function. If I look at letter B, let's say I drew a line right there. I have 1, 2, 3, 4, 5, 6 places where those points are all lined up vertically with each other. That is not okay. That means there's multiple outputs for that input. Letter C, any place I draw a line, vertical line, that's the only point that shows up. So letter C is also a function. Why don't you try to answer the last three by pausing the video and taking a second to think, and then check your answers when you're done. Function and E and F were not, you're absolutely correct. Remember, if we have 2 points that line up right above each other, that makes it not a function. So just to summarize some of this information, and again, there will be a note sheet at the end, but you could copy this down in your notes. These are some hints as to whether something is or is not a function based on the different representations. So we have table, mapping, and graph. On the right-hand side, all of these are functions, examples of functions. And on the left, these are all not functions. So take a second to read through this slide, write it down in your notes so that you can use this as an example as you're doing your homework. And let's use it to try a few problems on our own. Here are 4 examples of relations or points or ordered pairs, and I want you to think about those ideas or those representation rules we had on the last slide and determine which of these relations are functions. Which ones of these do we have every input going to exactly one output? Pause the video, give it a whirl, and come back to check your answers. Answer is letter A is a function because you don't have any repeating x values. And if you need to, you could always draw a mapping that represents that if it's easier for you to see. Letter C is not a function. Here we have repeating x values. So 3 goes to both -10 and -20, which makes it not a function. B is a function, very clear to see. This is also very clearly 1 to 1. If you were curious, ooh, I spelled that wrong, 1 to 1, because you have one arrow from the input going to one of the output. And then letter D is not a function because it does not pass that vertical line test. You have 2 points that are lined up on top of each other. Let's think about this. Vending machines, we've all experienced them. They're delicious. I want you to think about, are these pictures of vending machines functions? What would be the input or the output? And which one of these is 1 to 1 and why? Pause the video to take a second to think about it and come back when you're ready. Not just drool over the Rice Krispie bars in there. In that first picture, we do have a function. Every input, which would be the letter you would type in, letter and number to get the piece of candy, every input comes out with exactly one output. It is not a one-to-one function though, because you have multiple inputs that go to the same output. So you can see this here in this mapping. The second example is also a function. Every input will give you one item, but it's also 1 to 1 because you don't have any repeating items in the vending machine. It would be pretty shisty if they were to say, hey, if you put in C2 for your code, maybe you'll get, the cookies, but who knows what's behind there? You might get something else. So generally speaking, vending machines are functions. A couple last examples really quickly. We have this table, and what we want to do, we're talking about hours of studying and scores on an exam, is figure out, is the score on the exam a function of the number of hours you study? So is the score on the exam, that would be considered our output. Is our output a function of the input? Okay, I have this phrase up here to kind of help us out a little bit if you need it. What I would do is I would draw a mapping to figure this out. And I would say, all right, hours of study is my input. So that's 1, 2, 3, and 4. And my score is my output. So my scores are 60, 80, and 95. So if I go 1 to 60, 2 to 80, 3 to 80, and 4 to 95, I can see that every input goes to just one output so yes, this is a function. Looking at the next example, we're going to change the question slightly. Is the number of hours you study, so that's our output, a function of the score you get? So drawing a mapping, my input this time would be 60, 80, and 95, and my output would be 1, 2, 3, and 4. 60 goes to 1, 80 goes to 2, 80 also goes to 3, and 95 goes to 4. So as you can see, 80 is an issue here, so this is not a function. If they ask you to write this out as a phrase, you could use this as a model and fill in the values for input and output that they are giving you. Here's a quick glance at a note sheet. We will have this posted on Schoology as well. Please go ahead and complete your Pearson assignment, and we will see you again later.